All right, so we'll spend all of our time pretty much on just regular mass spec where we can just know to the ones place. However, there are high resolution mass specs, and these are much more precise. These are accurate to approximately the fourth decimal place. And the reason this is useful is that a proton and a neutron aren't actually the same mass. They're slightly different. So a proton weighs approximately 1.6726 times 10 to the negative 24 grams, while a neutron weighs 1.6749 times 10 to the negative 24 grams, right? And so you can see there's a difference here. And so if you can resolve the mass of these quite accurately, you can tell the difference between a proton and a neutron. And it actually gets even more complicated than that. If we think about deuterium, it has one proton and one neutron, and it weighs 2.0141 AMU. And then if you take a look at a carbon 12 atom, it has 6 protons and 6 neutrons, and this weighs exactly 12.0000 AMUs. And so if you think about this going to this, right, even though it has 6 times the amount of protons and neutrons, it's not multiplied by 6, right? If you multiply this 2.0141 times 6, you get a number that's actually larger than 12, right? The reason for this, it has to do with energy and mass conversions and really nuclear chemistry. We won't touch on it, but I can show you some playthroughs if you're interested in that. The reason that this is useful is if you have two compounds, maybe something like this versus something like this. They're both 84 grams per mole. However, and so you wouldn't be able to tell which compound is which based on regular mass spec. However, if you do high resolution mass specs, because the oxygen and the carbon weigh slightly different amounts because they're made out of different numbers of protons and neutrons, this one is 84.0573, while this one is 84.0936. Right? So you can tell if you've got a lot of resolution there, you can tell the difference by just looking at your molecular ion peak. We won't really be doing any of this.